Good afternoon. Today we're going to do a short review of formal proofs. Then we're going to again look at logic circuits as we started last time. And within logic circuits, we're going to do two things. We're going to figure out how to do some reduction of our logic functions. And we're also going to talk about disjunctive normal form, which I will write out again later. And you also have a homework problem on that. And we'll also start today on predicate calculus. So your current homework assignment has on it, the very first problem talks about this disjunctive normal form, and we'll talk today about why you need to know that. Okay, so last time we did some proof by contradiction and some direct proofs. So I want to remind you of what the sequence of steps are for both of those types of proofs, so that you have like a cheat sheet to look at while you're trying to do this. So, excuse me. So when I'm doing a formal proof, a direct proof, what I'd like to do is, the first thing I do is write my givens. And the second thing I do is look at the statement I'm proving. And I'll just call that the conclusion. I find a statement in the proof. So at this point, it's a statement in the givens, but in general, we're going to be using this rule. So we're going to find a statement in the proof that looks like what I'm proving. Oh, sorry, I wasn't showing you all of that. So I'm finding a statement that looks like what I'm proving. So for example, if I was proving P implies S or T, then I would probably look for a line in my proof that had P implies something or other. So I would look for this. Why wouldn't I look for something implies P?
They don't logical.
You can use addition rule.
Because the order really matters in implication, and if something implies the P, I know that that's not going to get me to have the P as the hypothesis of what I'm trying to prove. So I want to look for something that has the P in the right place, if I can find it. If not, I'll settle for any old P I can find. Okay, the very next thing I do after that is I'm going to call that line A. So the line that looks like what I'm proving, so it looks like the conclusion, I'll call that line A. So then the next step, that would be step 4, try to eliminate variables on line A that are not needed in the conclusion. So for example, if my conclusion were P implies S or T, that's my conclusion, and I found the line, let's say my line A was P implies Q or R. Now I would try to do something that would get rid of Q or R. So that means I'll probably have to use some other lines in my proof that might have Q or R in them. So let's suppose that I also had Q implies S and R implies T. So then I might want to somehow combine line A with these two to replace the Q and the R with S and T. Now let me show you a very cool rule that will help you do that. So does everyone see how I want to eliminate the Q or R, and in the process I'm going to try to bring in S or T. So usually those two things will happen at the same time because I usually give you proofs that you can do. So when you eliminate the variables you don't need, you usually end up incorporating the variables that you do need. Okay, so when I do this, let's just say these are my givens, lines 1, 2, and 3, and all of these are given. I know that I'm working with line A, but I might not be able to use it immediately. I just know that that's the one I want to combine with some other line to get what I'm trying to prove, to get my conclusion. So what I'd really like to know is that Q or R implies something else, and then I get to use my favorite rule, which is called Hypothetical Syllogism. Right? That's your favorite rule. Okay, so I would really like to have Q or R imply something else. Now I have Q implies something and R implies something. So I'd really like for Q or R to imply S or T. And then I would really be happy because then I would be really finished if that were true. Right? Well, it is true. It comes from lines 2 and 3. And the rule name, I'm going to write it in underneath this because I don't have enough room. Constructive Dilemma. Now this rule should make some sense to you if we go back and we think about implication as a less than. If we say that Q is less than S and R is less than T, and I add the left-hand sides and I add the right-hand sides, then the left-hand sum should be less than the right-hand sum. Does that make sense? Okay, so that's exactly what happens with constructive dilemma. It allows me to combine two implications to get a new one. So in this case, I used an OR. I ORed the left-hand sides and I ORed the right-hand sides and created a new implication. Do you think that I could also use an AND to do the same thing? I could. So what I have to do is just make sure that I use the same operator when I combine the left-hand sides and the right-hand sides. So if I wanted to take these two implications and combine them, I could AND the left-hand sides together and imply ANDing the right-hand sides together, or I can OR the left-hand sides together, and that implies ORing the right-hand sides together. So it works just like less than or equal to. Right, so now we have just one more line to go in this proof. And we have no more space. Let's do that. We have one more line to go. Now we can use our favorite rule with lines 1 and 4 to get P implies S or T. So that was 1 and 4 and hypothetical syllogism. So we followed our rules for direct proof by looking at what we wanted to prove, which was P implies S or T, finding a line that looked like it, P implies Q or R, and then we figured out a strategy to get rid of Q or R. And that brought in S or T for us in this proof. Okay? There are other ways to do this. We also had, last time we talked about using the simplification rule. Remember when we wanted to use hypothetical syllogism, and we just had, say, if we just wanted to combine lines 1 and 2, so if I had P implies Q or R and I had Q implies S, I could say, I couldn't do that. Another thing I could do, which I haven't talked about yet, is I could OR an R onto both sides. So just like a less than or equal to, I could add the same thing to both sides and the implication should still be true. Right? And that works actually just the same as constructive dilemma. So even though I'm done with this proof, I could also write a line in here that R implies R. That's always true.
When you're adding, don't you have to add to one side and subtract from the other?
No. If I have an equation or an implication, I have to add the same thing to both sides. And then
I thought that was only for multiplication, not for addition.
Let's do some math.
Yeah.
Okay? Let's do a little bit of math right here. If I have x equals y, then x plus 5 equals y plus 5. Yeah?
Okay.
So I don't want to subtract the 5 from one side and add it to the other.
All right.
So the equality is going to be still true if I do the same thing to both sides. So that's what lets me, if I have a logical equivalence, I can negate both sides also. But if I have a logical implication, I can't just negate both sides. Right? So just like this, if I have x less than or equal to y, I can add 5 to both sides. But I can't say minus y is less than or equal to y, minus y. Right?
Right.
So less than or equal to, it really makes a difference if I have a less than or equal to or an equal to. But constructive dilemma works like this. So I can do the same thing to both sides, as long as I don't negate both sides. If I did want to negate both sides, what would I have to do to the less than or equal to?
Inverse.
Reverse.
I would have to change it to a greater than or equal to, or in other words, reverse the order of the implication. Right? So I can also do that, but I have to change the order. Okay, let's go back to explaining the other rule that I was talking about. So again, in this proof, let's just suppose I wanted to combine lines 1 and 2. So if I want to combine lines 1 and 2, I need Q or R to imply something. And I have Q implies S. I'd really like for Q or R to imply S or R. Sounds like something reasonable also, because I just said if we have a less than or equal to, I should be able to add the same thing to both sides.
Line 6, what made you have the conclusion for line 6?
Line 6 is just a tautology. So that's one of your identities on your axiom list. It's something that's always true, because R implies R is logically equivalent to not R or R, right?
Yeah.
This is just a side note so you remember. And a variable ORed with its negation is always true. That's a tautology. So since this is always true, then R implies R is always true, and I can write it in any proof I want to. Anything that's always true, I can put into a proof. So this is an identity. Then I can combine 2 and 6 with my constructive dilemma the very same way I've used it before to get what? If I'm going to combine 2 and 6 with constructive dilemma, what do I get?
Q or R is equivalent to S or R.
I OR the left-hand sides, and that implies ORing the right-hand sides.
Yeah.
So Q or R implies S or R. And then now I can use line 7 along with line 1 to get what?
7 and line 1.
The
P implies S.
hypothetical
P.
S or R.
syllogism.
P implies S or R.
So if I use hypothetical syllogism, my favorite rule, I get to get that P implies S or R.
Show me how line 7 works again. I mean, I understood it when you did it in line 4.
Right. So it might be that it confused you that I put R implies R into my proof.
Well, I mean, that's only logical.
Okay. So now what I did is I took my implication in line 2 and my implication in line 6. So I took Q implies S and R implies R, and I combined them by ORing the left-hand sides of each of those implications. So I get Q or R, that's ORing the left-hand sides. So from 2, the left-hand side of 2 was Q.
Okay.
The left-hand side of 6 is R.
All right.
So if I OR them together, I get Q or R. And in the same way, I OR the right-hand sides. S is the right-hand side of line 2. R is the right-hand side of line 6. And I OR them together, I get Q or R implies S or R. And then that's using constructive dilemma again. Actually, I told you that hypothetical syllogism is your favorite rule, and it really is, but constructive dilemma is really my favorite. And the reason is because you can do these cool things and make your proof a lot shorter. Constructive dilemma really combines a lot of things at once. And so anytime you need to use it, it's really, really powerful. And if you need some extra problems for practice, say truth table practice or anything like that, you can take any of the axioms and prove them with truth tables, or you can also try to prove them like using other rules. So for example, let's do one more example.
Addition rule. The addition rule you changed, did you say, is this logical equivalent or implies?
Right, the addition rule is a logical implication. So that was changed on the axiom list. So I did pass one out. The addition rule is a logical implication. And that was a typo in the initial version of the axiom list. So now it's in the top part of that handout. So it's one of the logical implications. It's not a logical equivalence. So please, if you have printed out the axiom list, please print it out again because I renumbered the axioms. Okay, so the addition rule was P logically implies P or Q. So anytime I know that P is true, then I know P or Q is true. We know that's not a logical equivalence because P or Q could be false. Actually, it's going to be true whenever P is true.
Yeah.
But that doesn't mean, but just because P or Q is true doesn't mean that P is true. Because this statement may be true because Q is true and not because P is true. Yes?
How come on this list I don't see conjunction in here?
You don't see conjunction.
Should that
It's
be
not on there.
Does anyone else see conjunction on the axiom list?
Not
Not on there? Your TA will be flogged later. Okay, I'll put it on there. So the conjunction rule should be on the axiom list. So the conjunction rule says that if I know P and I know Q, then I know P and Q. So if they're on separate lines, I can put them on the same line together.
There were a couple other ones that were mentioned either in the reading that I didn't see on the list. Absorption?
The axiom list that I have on the webpage and on this handout is the one that I would like for you to use for your proofs. So there may be other ones in textbooks that you look at. There's actually lots more rules. But I've reduced this down because these are the rules that are the most useful for you. So they're names for other rules and other things that are true. But that doesn't mean that I have to have them on the axiom list that I want you to use for proofs. So I want you to use these because I believe that these are the most useful. And this is a small set of things to remember. And I want it to be as small as possible so that when you're doing your proofs, you're thinking about what you're proving instead of 55 axioms to remember. Okay. So if you want to use other rules, you can. But these are the ones that I would like for you to know. Another question?
Yes, using the addition rule, so if we want to change a P, we know P is true, and we want to have the end result be P or Q, we don't have to have Q on a line by itself because it doesn't.
No, we don't have to have
necessarily
Q at all because since we know that P is true, we know P or Q is true regardless of the truth value of Q.
Okay, so we can just add it.
So that's the difference between the addition rule and the conjunction rule. If we look at these two, the addition rule only requires that I have to have P, and then I can conclude that P or Q is true. Conjunction can only happen if I have P on a line and Q on another line, and then P and Q must be true. So the conjunction rule we really only use it this way in a proof, right? Because if we use it the other way, if we say P and Q, and we want to conclude that P is true, what's that rule?
Simplification.
That's called simplification. And it doesn't go both ways because we're just concluding that one of the variables is true. So we don't usually use the conjunction rule backwards. We just use it one way, even though it's a logical equivalence. Actually, let's just use it going that way. And simplification will go that way. So it will go the other way. Okay, so in the methods of direct proof, we had four steps. So let me write them again in shorthand. So the very first one was write the givens. And we look at the conclusion. Find a lookalike. And eliminate unnecessary variables. So that's our process, and we keep repeating that. So this is a method for doing direct proof. And I'd like to give you the same thing for doing indirect proof. So again, we write our givens. But what's the next step in a proof by contradiction?
Negation of the conclusion.
Negation of a conclusion.
Then we write the negation of the conclusion. Then after we write the negation of the conclusion, we apply De Morgan's, if possible. Well, it is possible. But what might we have to do first? You can only apply De Morgan's if we have an and or an or. But if we have an implication, we'll have to do another step before we can do De Morgan's. Right? So you may need to use implication rule also. And then we simplify if we can. So what operator do I need to have if I want to do simplification?
And.
I need to have an and. So if there are no ands, I can't simplify. So if it's possible, I simplify. And these two things, actually these three things, give me my money. So the pieces that I end up at the end of that, that's what I call money. Now I combine my money, I take it to the store, which is the givens. So I combine it with the givens repeatedly until what?
No more money.
Until I find
Contradiction.
until I find a contradiction. In other words, until I find a variable and its opposite. So any variable or statement and its opposite anded together will give me a contradiction. So in a similar way, I'm going to repeat these steps throughout my proof by contradiction. If I get a statement that has a not in front of it, I'm going to apply De Morgan's and simplify every time I get a chance. So not just the negation, the conclusion. Anytime I have a statement that has not, parentheses, P or Q, something like that, I'm going to do De Morgan's. I'm going to simplify to get the pieces, because it's much easier to see that P is the opposite of not P than it is to see that not P or Q is the opposite of P and not Q. That's a lot harder to see. So if I simplify as much as possible, then it's much easier to see two things that are opposites. Okay, so I wanted you to have these two lists to write down so you have some guidelines when you're trying to do your proofs.
You had mentioned that there's, besides contradiction, there's other types of indirect proof.
Yes, there are other types of indirect proof. In this class, usually I mean proof by contradiction.
Okay. So in homework, number 7, you mean contradiction.
Yes. So you can do other types of indirect proof. So if you're comfortable with doing them. So another type of indirect proof would be proof by contrapositive, right? So there's usually only 3. Usually we do direct proof, proof by contradiction, or proof by contrapositive. So what do you think that proof by contrapositive is?
If you can prove that either your conclusion or its falsehood, or its negation, I guess, is true.
So here's the statement that I'm proving. Direct proof assumes P and shows Q. By contradiction, assumes P and not Q and shows 0. Right? It shows false. By contrapositive, what does the contrapositive rule say? If I have P implies Q, that's logically equivalent to not Q implies not P. So by contrapositive would be proving the statement not Q logically implies not P. So you would assume not Q and show not P. So that's another method of proof, which we haven't done, but you can do that perfectly legally. Any method which proves the statement if you have your givens and your conclusion, any method that's logically equivalent to this can be used as a proof method. So what would be another method that you could use, although it's not used very often? I know another statement that's logically equivalent to P implies Q. What is that statement that we use the most?
Not P or Q.
P is not P or Q. So if you could show that not P or either P is false or Q is true, so another method would be to show either not P or Q is true. So if you could show some way that that was true, then you would also have your proof done. Right? So if I wanted to prove that if I have $1 million, I'm going to give each one of you a part of it, all I would need to do is either show that I don't have $1 million or that each one of you receives some money. Right? So I could do a proof that way. So there's lots of ways to do proofs. In this class, we're normally going to use the first two. They are the easiest. Proof by contrapositive is usually a little difficult because the conclusion usually has fewer variables. And to figure out that the P is true or not P is true from not Q is going to take using the addition rule and a lot of other things that are not as natural as doing proof by contradiction. Are there questions about this? Let me tell you something interesting about proof methods before we go on. And remember that I told you that one reason why we were doing proofs in the first place was that if we wanted to build a knowledge system on a computer, we would want ways to represent knowledge and then ways to derive things from what we know, right? When we do that on a computer, the first logic proofs were actually not direct proofs. They were indirect proofs. They were proofs by contradiction. Why do you think that is?
Easier to prove false than it is true.
It's a lot easier for a computer to look for a false than it is for a computer to look for P implies S or T. Okay? So it can just check every statement and see if it's a 0. And if you haven't got to 0 yet, you know you're not done. If that's a lot faster check than it is to look at every single line and see is the first variable P, then is there an implication sign, then is there a parentheses S or T. So that's why we have, that's why actually computers use proof by contradiction, because a lot of times if they're doing these proofs, because it's easier to tell when you're done. But for people, since we can look at either 0 or look at P implies S or T and very quickly see which one, that we need to see, it doesn't matter which one. Just sometimes a proof is easier, direct proof, and sometimes indirect proof is easier for a person. Okay, so are there any more questions about the formal proofs? Or the truth tables, actually, if anyone has any truth table questions. When you're doing your truth tables, do remember that implication is just like less than or equal to. Because I know a lot of times you're going to be looking at truth tables and you're going to see a 0. You're going to be looking at P implies Q, and you're going to look at the value here and look at the value here, and really you're going to want to write a 0 there because P is false. Right? But it's not. What's the value here? It is 1. Okay? So remember that implication is like less than or equal to when you're doing your truth tables. That's very important. Okay, so let's go on and review the logic circuits that we started in the last class. So we have 2 gates that we use, and an OR gates. And we also changed our representation of writing ands and ors to make them easier to read. Okay, so and we were just going to use a dot or nothing, and or we were going to use a plus. And what do we use for not? So not, we were using a bar over the variable. Okay, so, and we also had 3, actually we had two input gates and we had one input gate. So this was which gate? This is the AND gate. And what does the OR gate look like?
curved and sort of pointy?
Half
The
a
back
cylinder.
is curved, and it can be sort of pointy. Although you should still recognize that if the back is curved and the front's not, like not pointy, it should still be an OR gate. Okay? So then, what does the inverter gate look like?
Triangle with a circle.
It's a triangle with a circle on it, and it has how many inputs and how many outputs? One input and one output. And which side of the diagram is the inputs? The left-hand side, and the right-hand side is the outputs. And why do we do it like that?
Convention.
One output
And
can be another.
the inputs
Right.
for the
That's a
next one.
convention because that's the way we read in English. So we go from left to right. And now the rest of the world has to put everything left to right also. Okay, and this was a NOT gate. And what do we normally do with NOT gates also?
Use them to change ands to ors or ors to ands.
We can use them to change ands to ors and ors to ands, but we also don't usually write this whole gate, right? We just use the bubble, the little circle. We call it a bubble, and we just use that instead. So the less we have to do, the better, right? So let's make up a circuit and derive the logic function for it, and then we'll see if we can do any reduction on it, okay? Actually, I have a function here. Anybody confused yet? What did I just do?
Three
variables.
I made a 3-input AND gate. So it's still an AND gate. Still the inputs are on the left and the outputs on the right. So I've just ANDed 3 statements together instead of 2. And why is that okay?
Because it's and?
You're the teacher.
Because it's and I use the same operator on both of them. So and is associative, so it doesn't matter which order I AND the things. It's all going to be the same. P and Q ANDed with R is going to be the same as P ANDed with Q and R, and all of them ANDed together at the same time. So we can use multiple inputs in our gates and make things look a lot simpler, and I don't mind if you do that in this class. And I'm going to do the same thing with an OR gate. See, I forgot to make it pointy, but you still know this is an OR gate. Let's call this X, Y, and Z. Some of your circuits class will make you put X, Y, and Z in one location on the page and then draw lines to where they go. But I don't mind if you just label the inputs right next to the gates. That's what I like to do anyway. So you can draw your circuits however you like. I'm going to be lazy and put all the inputs right next to the gates. Okay, so first, what's the output for the first AND gate here?
Not X.
Not X,
And not Y.
not Y,
And Z.
Z. What's the output for the second one?
Not
X and Y. Not X.
Not X, ANDed with
And Y. And
Y,
Z.
and ANDed with Z. And the last one is
X, not Y, not Z.
No.
X, not Y, not Z. Now all of those are now inputs. If we follow the lines, they're now all inputs for this OR gate. So my OR gate is just going to be not X, not Y, Z for my first gate, ORed with not X, Y, Z, ORed with X, not Y, not Z. So that's writing my output for this function, and this is the final output. Are there questions about that? So if you follow from left to right, you follow the diagram, you shouldn't make any mistakes. And you can draw right on the diagram. So you can just follow your lines through and you'll always get this correct. And that's why we don't spend a lot of time on logic circuits, because if you do exactly, you follow everything left to right, you should be able to do it. Okay? Now what we'd like to do is reduce this to something that has fewer gates. Okay, so I'm going to write this function on another piece of paper, and then we're going to reduce it. How do you think we might reduce something?
Cancel out.
Combine.
Well, we're going to have to use things that we know about and or, right? And we're going to have to use we're going to have to use distribution in order to sort of rearrange things so that we can see where we might be able to get rid of some variables. So I'm going to magically tell you that we're going to look for something that we can factor out of two of these terms. So what might we be able to factor out of the first two terms?
Not X.
So Z is in both of them, I heard someone say, and not X also is in both of them. So let's write X, not X, Z, factor it out. So that means we're left with not Y in the first term plus Y in the second term. And then we leave our final term as it is. So this was by the distribution law or rule. Now what do we know?
Y, not Y, is always 1.
Y ORed with not Y is what?
1.
It's always true. Either Y is true or Y is false. So this is always true. So, and this is how I really do these problems. I put a 1 under things that are true and then replace them in the next statement. So 1 multiplied by something gives back to something I multiply. So I get back xz plus x, not y, not z. Now I know I'm done factoring when I can't, I know I'm done reducing when I can't do any more factoring. So this looks pretty reduced, right? Because there's no common variables in either one of them. So now this is how many gates? Assuming you can use multiple input gates.
3.
It's now 3 gates because I have to have 1 gate for this, 1 gate for this, and 1 gate for that. Okay? So if I had to draw that, I would draw 2 AND gates. I'd put not x, z here, and then x, not y, not z. And then I'd feed those both into what kind of gate? An OR gate, which has a curved back. And that would be my final output. So we did a reduction of 1 gate. We didn't need one of the gates, and we also reduced one of our gates to a 2-input gate, which is simpler logic-wise. So let's make a list of some of the things you might look for when you're doing reduction. Okay? So we already saw one of them. We were looking for y or not y. That's logically equivalent to 1, right? What's logically equivalent to 0?
Y and not Y.
Y and not y is logically equivalent to 0. Now what would y times 0 be?
0.
0, because of the way and works. What is y times 1?
1.
That's logically equivalent to 1. What about y plus 0?
Y.
That gives me back y. What about y plus 1?
Y plus
1.
1.
1.
It gives me 1, because in logic, anything ORed with a 1, so this is where our plus for OR gets us a little confused because we don't actually increase. We actually just stay at 1 if we do y plus 1. What about y plus y? What is that?
Y.
That gives me y. That's y or y, so I can simplify that just to say y. And what about y times y?
1.
And
1,
No.
I think.
If you're not sure, just check all the values of y. right? So if y is 0, then 0 times 0 gives me 0, right?
That's y.
If y is 1, then I get 1 times 1, which gives me 1. So the logical output of this is logically equivalent to y.
Y.
Whatever I put in is whatever I get out. And that works because 0 and 1 both squared give us back the number.
I have a question about your fourth one down. Y1 is equivalent to 1. Wouldn't that be y1 is equivalent to y?
Y times 1, you're right. That's equivalent to y.
Okay.
Thank you.
And I just wrote it down exactly how you did.
Okay, and these are some identity rules. These are called idempotent, which I don't like the name, but that's what they're called. And these are all on your axiom list. And these are all identities. Or these are either identities or they're just basic truths because of, oh, I know. These are called identities, these last few. And the top one's called tautology. And the second one's called contradiction. So all of these are on your rule sheet, and they're also listed in Chapter 9 of your textbook. Chapter 9 of your textbook also has Karnaugh maps, which is another way to do reduction. It's actually the very same way we just did. It's using all of these rules, but it does it with a cool picture. Does anybody want to see that? Yeah? We're just going to do this briefly for entertainment value. I don't want you to use Karnaugh maps in this class. But I will show them to you because you're going to do them later, and I'll tell you why they work. Okay? So for this problem that we just did, we'd want to make a diagram. A Karnaugh map is a diagram. It's a tool. It's a way of drawing a picture so that we can see when we have the same term in two terms. That's all that it is. So the way you do your diagram is this. Across the top, you do pairs of variables, and then down the side, we'll just do our third variable. So this is going to be z, and this is going to be not z. So we have to put all the combinations of anding our variables together. So we have x, y. Then we're going to do not x, y. Then we're going to do not x, not y. And then we're going to do x, not y, because we need all the combinations. And the order of those mattered because if you look, adjacent ones only differ by exactly one thing. So these two, if I do a multiplication row by column, it's going to be x, y, z in this one. Then this one's not x, y, z. So these two adjacent ones only differ in one bit position. So same thing here. These only differ with y. One has y and one has not y. And same thing this way. This differs z and not z, and so on. So in the function that we just had, that was not x, not y, z. So I have to put a 1 right here. So I'm going to put a 1 wherever I have this term. Okay? Then I have not x, and then yz. So I have a 1 right there. Then I have x, not y, not z. So x, not y, not z goes right there. So now, and then in the diagram, I look for clusters of things. So things that are adjacent to each other. And actually, in this diagram, these two things are adjacent too. So the ends wrap around. Okay, so, but you can rotate your diagram also to see that. So like you could relabel the rows so that you could see this one was adjacent to that one also. But here I see a cluster, and then I see what's in common between those two. So what's in common between these two? What are the same?
Not x.
So not x is true in both of those, and so is z. So these two together are logically equivalent to not x, z. And that was the same thing we got by factoring out the first two terms, and we got not x, z, because we got that it was not x, z times y plus not y. And if you look at the diagram, you'll see that we have not x, z times y plus not y. And this can't be reduced because it's not adjacent to anything. Right? So that's plus X, not Y, not Z. Isn't that cool? I think it's cool. Okay. So if you want to do reduction, you can use a Karnaugh map, but then you need to show me why it worked. Okay? So the reason why it worked is because you found a cluster that things were in common, and you should have been able to factor out a Y plus not Y. And that's what I want to see on your homework. Although you can use this to show yourself what the most simple fraction is. So let's draw another one and just make it up. Make one up and then see if we can do a reduction on it. Okay, so here's an example function, and we're going to try to reduce it. What's the biggest cluster that you see?
Z, the whole Z.
All ones across the top. And what do they all have in common?
Z.
Z. So this is really, if I had to write it out, it would be Z times this, plus Z times that, plus Z times that, plus Z times that. Right? But this is just Z. So that's cool. That's Z. Now, I could just write this term down, but it actually is adjacent to something else, right? So I can have it use fewer variables by noticing that it's really adjacent to this also. So what's in common between these two?
X, Y. X,
Not X.
Not X.
Not X, not Y. So there's my reduced function there, but originally, if I had to write it out, it would have 5 terms. These are called min terms. And min terms are all the combinations of anding the variables and their opposites. Right? Because in this table, I should be able to find x, y, z, not x, y, z, not x, not y, z, and so on. So how many things should be in the table if each variable has 2 possibilities? There's 3 variables, and each of them have 2 values.
So 8.
Should be 2 cubed, which is 8. Because it's 2 times 2 times 2. It's 2 per. So I have 8 things in the table, and that makes me feel better, because it has the same number of rows as my truth table would have. So I can represent any function in a Karnaugh map. Right? So let's go back to the truth table and see what that looks like. So you can look at Karnaugh maps some more in your textbook in Chapter 9. It has a little bit, and you can make up functions and have fun reducing them that way. Okay. But let's make a truth table and talk about what these min terms are and why it's important for you to know them. So if I have 3 variables, I need to have 8 rows in my truth table. So these are going to be my inputs. And how do I write my variables? Is anyone going to remind me? I forgot.
0, 0, 0, 0. 4 zeros for X.
I should put zeros and ones, right? So I put 4 zeros for X
And 4 ones.
and 4 ones. And then what do I do for Y?
2 zeros and 2 ones.
2 zeros and 2 ones.
Twice.
2 zeros and 2 ones.
And then the last one alternates, right?
2 ones.
I guess I remembered.
That's really.
Okay, now remember our min terms. That was all the combinations of anding the variables together. Okay? Those correspond to each one of these rows. Right? So which one corresponds to the first row?
Not X, not Y, not Z.
How about the second row?
Not X, not Y, Z.
Not X, not Y, Z. The third row is not X, Y, not Z. I think you might be getting the hang of it, so I'll do a few by myself. What's this one? What's the fifth one?
X, Y,
Not X.
Z.
Oh,
X,
X, not Y,
not
Z.
Y,
X,
not Z.
Z.
The next one is x not y, z. The next one is x, y not z. And the last one is x, y, z. So those are all 8 of our minterms. And the reason why we do minterms is if I want to use Karnaugh maps, I need to use minterms. I have to know what the function is using minterms and not something else, right? So I have to be able to write any logic function in terms of minterms if I want to use Karnaugh maps to reduce them. So even if I might know a simpler function for it, I'm going to get the simplest possible function by using the minterms and then doing Karnaugh map reduction. Okay? So let's make up a function.
Did you get that? Okay.
So let's say a function f, and I'll put some values in, and we'll figure out how to write it with minterms. Okay, each minterm is an and an and has how many ones in the truth table? Just one. So the actual truth table for not x, not y, not z is going to have exactly one 1 in it, and will be in this row, right?
Say that once more.
Yeah, say that again.
If I made a truth table for not x, not y, not z, it should have a 1 here and zeros everywhere else.
Yes.
Because that's the only time that it gets to be true, is if x is false and y is false and z is false.
Cool.
Yeah, it is cool. Okay? That's why we have minterms. Because with minterms, we can combine them with ors to make any function that we want. So anytime we're given a function like this, without being really smart, we can write a logic output function without very much thinking, as long as we know what minterms are and how to use them. Okay? So the ones that have ones next to them, that's the ones I'm going to use the minterms, and I'll OR those together. And that will give me the output function. So using that, let's figure out what f is.
Not x, not y, z.
So f, I'll just number these, and then you can tell me which numbers they are. So f equals what?
2,
2 ORed with
3,
3,
5,
ORed with 5,
6,
and 6,
7.
and ORed with 7. So I'll write down under these what they are: not x, not y, z, plus not x, y, not z, plus I go down to the 5th one, x, not y, not z. The 6th one is x, not y, z. And the 7th one is x, y, not z. And I think it would be fun to make a Karnaugh map for this and see if we can reduce it. Okay?
Could you go back to how you got the values for f again?
How did I get the values for f? I made it up.
Okay.
That was a really good question. I just made it up. Off the top of my head, I just put a random function. This is to demonstrate that no matter what the function is, you can come up with a minterm function for it, and you can do Karnaugh map reduction. Okay? And this cool thing is called disjunctive normal form. Is if I OR minterms to make a function, that's called disjunctive normal form. Let's write the name of that because it's important. Disjunctive normal form. It's called disjunctive normal form because it's adding lots of terms together, and the terms, disjunction is OR, right? Mm-hmm. So I'm ORing lots of terms together, and all the terms are ands. So disjunctive normal form is ORing together lots of and statements. Okay, so if I were to take this whole thing and then put parentheses around it and AND it with something else, it would no longer be in disjunctive normal form. Because it would actually, the main operator would then be an AND. Right? Here, all of this is an OR, and if I drew a logic diagram for this, the very last gate would be a huge OR gate. Right? So if I had to just draw this straight from this, actually let's draw the circuit for this, because you're going to have to do that on your test and on your homework. You're going to be given functions like this, and you have to draw a circuit for them. The very fastest way is to find the minterms, write it out, and then draw gates. multiple input gates for these. So how many AND gates will I have?
5.
5. So I'll draw 5 gates. Hopefully these don't look like anybody's grades in here. Oh, that just fell right flat. So when I'm drawing this, I'm just assuming I'm going to put X, Y, Z down all of them. And then I just draw bubbles where I have knots. And then I'm going to take them all and feed them into OR gates. I have one big OR gate. And the output is F. So and then you can double check your work by checking each minterm and making sure that the gate implements the minterm that you wanted it to. So I can go back and check my work by writing out the minterms next to each gate. And then double checking that those are the ones I really wanted to have. So there's no reason for you to write a diagram and not know what the output is, because you can always check it yourself. So the F is the sum of all those. Yeah, I'm cheating. Okay, so that's how we draw a circuit for that. So when your grader's grading your paper for the test and I give you a function and say, write the logic function for this and draw a circuit, this is the circuit they're going to look for first, because this is the easiest one to draw, to get. As soon as you look at the diagram, you can just draw it right away. Okay? We like things that are fast, right? You don't want to waste your time. Right. So since I think it's cool, we're going to do a Karnaugh Map reduction of this.
Using your slides, show us how it would appear to us on the test.
How it would appear to
Yeah,
you
you
on
don't
your
have to
test?
rewrite it all. Just kind of use the slides that you've written. So you'll give us.
It would look just like that.
Okay.
That's what you would be given on the test. You would see that these are your inputs, F is your output, and I would say, give the logic function for F and draw a circuit that implements F. And that would be the problem. Yes?
You wouldn't want us to reduce anything.
No. I'll usually put do not reduce in big fat letters and parentheses. But I won't, like if you do want to reduce it, like you've done your whole test and you feel like, oh, I like Karnaugh maps and you want to play with them, go right ahead. But this is the function that I gave you. This will be the one that I'll be looking for. And I may actually even say, write it in disjunctive normal form. So I might ask you a question that says, write the following function in disjunctive normal form and implement the circuit from that, do not reduce.
So then we can just write the numbers down.
You could just write the numbers down, but you still have to have the correct diagram underneath.
So if we just wrote 3, 5, 6, and 7, whatever.
You have to label them.
6 and 7.
You'd have to go and
Label them up
label the rows. I don't mind if you use numbers. If you use shorthand, as long as it's clear what it is. You can write on the top of your homework, let X stand for P and Q, and everywhere you put X, that means P and Q. That's fine with me, as long as you have written down what you're doing. Because in this class, we're all mathematicians, and mathematicians love shorthand, but you have to make sure that everyone knows what shorthand you're using. So you can't use it unless you write it down. Questions? So we didn't use a lot of these, right? There are 3 of them we didn't use, and why didn't we use them?
Function doesn't call
F
for
had zeros where those minterms were, so we didn't want to use them, because if I ORed all of the minterms together, what would I get?
8 gates.
I would get 8 ones in my truth table, which would be a tautology, which would be a totally useless function to implement, right? Because I don't need any gates to implement that. I could implement it with P or not P, right? I could just stick that into an OR gate and get a 1 anytime I want. So I don't want to use all 8 of them. I always want to use less of them. So I wanted to point that out because you might get home and forget what we did and go, why don't I use all of these? Just write them down, okay? I had a professor one time that made everything look so clear while they were doing their lectures, and you would sit there and go, yes, 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 I believe, you know. It felt like you were in church or something. And then you would get home and try to do your homework, and you wouldn't have a clue because he never made any mistakes, so you didn't learn how to fix when you make mistakes. So that's why I mess up a lot up here. Okay, I have good creative excuses for everything. Let's do a reduction on this. It's got to be able to be simpler than that, don't you think?
Yeah.
So let's make a Karnaugh map. And remember that when we make our Karnaugh map, even if you forget how it goes, you can start with x, y, and then remember that the next column has to be just one different than that. So I could put x, not y, in the next column. It doesn't matter how you write them, as long as they're different by just one. The next one would be not x, not y. And the next one has to differ by 1 and be the one that's we didn't do yet, so it ought to be not x, y. And this one's going to be z and not z. Okay, and then we need to put 1s where we have 1s in f. So we have a not x, not y, z, so that goes here. That's the first one. That was 2. Let's just label them to make sure we do all of them. Then we have not x, y, not z. So that was the number 3 one. We have x, not y, z. That's this one. That was the 5th one. And then we have x, not y, z, x, not y, z. Oh, I just did that one. X, not y, not z. Oh, so this was 6, actually, right?
And 5.
And then this is 5.
Right.
So you got to be careful when you do these. X, y, not z. See, I'm just making some mistakes, so you'll be able to fix them later. Okay, so we have 5 1s. I feel pretty happy about this. Now I have to find clusters of things, and remember that these wrap around too. Okay? So actually these 3, right, kind of cluster together. And these 2 cluster together. Right, so we can reduce this. What do these 3 have in common? We have to figure that out. All of them have not z in common. So let me move this and so we can work on this by itself. So this bottom one has not z, but they also have something else. These both have x, and this has y.
I think
So-
7 and 3 would be better.
7 and 3. Maybe I can't put them all together.
Yeah, you can put all of it.
So probably, yeah, so I don't use Karnaugh maps a lot, so I'm not sure if I can use 3. Maybe you just have to do 2 and 4. Okay? So let's just do that. We'll just put 7 and 3 together. Okay, so 7 and 3 have y and not z together, right?
X, Y,
And then we'll put 6 and 5 together to get this one. So this was the 7 and 3 one. And then 6 and 5 together have what in common? X, not y, because they're both in this column that's under x, not y. And then these 2 together, which are 6 and 2,
Z, not Y.
Z, not y.
they have z in common and not y in common. So that's a lot simpler. We just need how many gates for this?
5.
We need 1, 2, 3 gates for each of those, and we could use 1 gate for the OR, assuming that we can use multiple input OR gates. Okay? So we have 1, 2, 3, 4 gates. And how many gates did we have before? We had 5 AND gates plus an OR gate, so that was 6 gates. And these also are just 2 input gates. These ANDs are just 2 input gates instead of 3 input gates, which is nice. Okay, so your boss would give you a big pat on the shoulder
So you
for
could
reducing
just,
this.
you could take this now, this reduction, and you can
We can draw a circuit for this.
logically imply that this is the same as that big long function that we just did.
Yes, it is. It's logically
All
equivalent
you've
to the
done
big
is
long
reduce
function.
the
Right.
function.
I've just reduced the way I've written it. So, yeah, we could. We can make a truth table and show that they're the same. So let's do that. That's a good idea. What's your name?
Groupings again?
Brian. We can all thank Brian for giving me a good idea.
Could you show me the groupings again one more time?
Okay, I did 7 and 3. I wrote them down here. So 7 and 3 were together,
3. Okay.
and I did 6 and 5 together,
Okay.
and 6 and 2 together.
Shouldn't you also? Okay. I was looking at grouping 7 and 5 together too.
I could group 7 and 5, but since those ones are covered, I don't need to do them again.
Okay.
So what you need to do when you write down your function is make sure that all the ones are represented by some grouping, and if they're not, you need to write it midterm just for that one. Yes?
You can't factor the not y out of the last two terms?
I could, and that would reduce the number of gates, but it doesn't like give me any less terms, sort of. So I could put not y, so I wouldn't have to put not y into two separate gates. So what he was saying is I could put not y times x plus z over here, and then I would just have y times not z.
Which doesn't make it any less complicated.
But it doesn't make it any
Doesn't
less.
reduce any factor.
Right, it doesn't make it less complex, and that's why I didn't do it. Okay, so let's show that this is the same. So we'll make a truth table for that. So the function that we just came up with didn't have an x at the beginning. It had a y, not z, plus x, not y, plus z, not y. So let's make a truth table for that. We'll make columns for each of these. Let's put brackets around this. Okay, so for y not z, I have to put a 1 whenever y is true and z is false. So I look for y is true. Let me make some rows over here. So I look where y is true and z is false. That's true in the third row, and it's true in the 7th row, and it's not true anywhere else, so I can put zeros everywhere else. Now, does anyone feel bad about there being 2 1s in this and statement?
No,
Why not?
because that's what our Karnaugh Map showed.
Y not z has 2 1s. Remember that ands, we kept saying they have just 1 in the truth table. 1, 1, right? So a 2-input and has just 1, 1 in a 4-row table. But since this is y not z, it has 1, 1 when x is true and 1, 1 when x is false. Right?
Cool.
That's why it has 2 1s in this table. So if I had another variable, like if I had 4 variables and this was still just 2, I would have 4 1s. Right? Because I'd have twice as many rows. So it would basically repeat this again if I had one more variable. So ands have just 1 1 in the truth table that only has the variables that it comes from. But when I add more variables, I have to repeat it. Okay, so x, not y, I'm going to look for x is true and y is false, and that's true in these two and false everywhere else. And then in the last function, I have z, not y. So I'm going to look for z being true and y being false. And now I'm getting used to it. I know that I'm going to have 2 of these. And zeros everywhere else. So let's OR the first 2 together. And then I'm going to OR these 2 together. Because I want to get this whole thing ORed together. So I get 0 or 0 gives me 0. 0, 1 gives me 1. 1 or 0 gives me 1. Hopefully that's going to come out with the same thing as f, because that's what we said after we did a reduction, that should give us f. So we'll put a logical equivalence row right here. Luckily I was smart enough to accidentally leave a space there for that. Okay? And see, is this column logically equivalent to f? So the first row, they're both zeros. That's true. Second row, both 1s. Third row, they're both 1s. I'm feeling pretty good about this. And we get 1 there. There's the same there, and false there. Oh, sorry, that's a 1. Because they're both false. So that's a 1. So I feel good because f came out with the same thing as my Karnaugh Map reduction. So you have many, many ways to check your answers when you do these problems. You can do truth tables, you can do reductions, you can use min terms, anything.
What are you ORing there in the OR?
This one?
The two of them. The first one.
This one?
Yeah.
These two that have brackets around them, the adjacent
Oh,
ones.
that. And then the second one.
The second one takes this one and that one.
Why are you doing that?
Why am I doing that? Because my overall goal is to OR everything together.
Okay.
I wanted to OR all three of the terms together, and OR only works with two things at a time, right?
Oh, this. Oh, got you.
So I ORed the first two and then ORed that with the last one. Sorry, I should have labeled those. So this is one. Let's just call this 2. So this OR right here is 1, OR 2. Now we've talked about disjunctive normal form. And if you remember, I said that one of your homework problems has the disjunctive normal form on it. Your very first problem on your homework is to write the disjunctive normal form for every single possible output function of 2 variables. Okay, so that's what your first homework problem is. So if I have P and I have Q, I can do min-terms for any truth table. So what are the min-terms for this truth table? So the very first one is not P. Sorry, let's draw the bars. Not P, not Q. The second one is not P, Q. The third one is P, not Q. And the last one is PQ. So any function that I come up with, I can write in terms of these 4. And that's what I want you to do on your homework. Now, an advantage for my grader for that is anytime there's a function, if everybody writes the solution with min-terms, then everybody's solution is the same, right? If you don't do like that, then everybody has a different one, and your grader has to take 3 times as long to grade your papers. But I also, the other reason for doing that, besides making it easier to grade, is I wanted you to have practice writing functions in terms of min-terms. Okay, so let's do one example. So how do I write this one with my min-terms?
Not PQ.
PQ.
P not
Or
Q.
P not Q.
So this is an example of solving one of your homework problems. You have an output function, you have min-terms to write them with, and you can OR the min-terms together to get the final solution.
Okay.
We did a lot today. Your homework is due, in a week or so. We have office hours on Tuesday and Thursday from 5 to 7 in Daniels 132, and that is also in your syllabus and your handout. It's also on the website. So if you want to come see Andy, and I'm usually there too. So if you want to come see Andy, you can do that. And we have office hours near class too. So check your handout for when office hours are and get started on your homework. I'll see you next time.